Hello, welcome to the video. In this lesson, we're going to be taking a looking at section 10.2, where we're going to be graphing cube root functions. So in 10.1, we looked at square root functions. So 10.1, we looked at square root functions. So this was like our parent square root function, f of x equals the square root of x. One of the one of the main concepts or big components of graphing a square root function was there was like a starting point, because you couldn't use certain values for x. Like in this one, you couldn't use anything. You couldn't use any negative number because it would make our function undefined. So the big question that we have to ask ourselves in today's lesson is there any value for x with a cube root of x? Is there any value for x that's going to make a cube root inside the cube root undefined? Which means if x was a positive number, what if x was 0? Or what if x was a negative number? I would encourage you guys, I would encourage you all to test it out. Um, if for some reason your calculator doesn't have cube root capabilities, I would suggest to do something like this. So whatever value you choose to as for x, there should be a little symbol like this, and then you could write it in as 1/3 power. So little little bit of information. The cube root of x is the same thing as writing x to the 1/3 power. Both of these mean exactly the same thing. Okay, they mean the exact same thing. So if you don't have cube root capabilities on your calculator, that is how you would address that. So when you are looking at a cube root function, we have, it says we have the capabilities of choosing any value for x to get a result for y, or f of x. So that is why if you look here in this core concepts, our domain and range is going to be all real numbers for this function. All real numbers for this function. So if I were to make a table, and if you look here, if x was +1, if x was 0, if x was -1, I would be able to get a solution for each one of these values. So like it says here, when x is 1, well, the cube root of 1 is 1. So that means y is 1. X is 0, the cube root of 0 is 0. So that's why y is 0 in this case. And same thing when x is -1, y is also -1. And you'll get other variance answers if you don't use 1 or -1 for those said solutions. What I would like you to keep in mind is just kind of taking a look at where the graph is located for for this function. It kind of starts off in like quadrant 3, and then it kind of goes upward, kind of like a curvature. It's not a line, it's kind of has like a kind of a curvature field similar to our square root function value. And then it crosses at 0, 0, which in this case is where our graph goes from quadrant 3 to quadrant 1. So that is kind of how the look of a cube root function is represented, and then it changes its look depending on, vertical and horizontal stretches, and the positioning of where it crosses by, the certain translations. And the translations that, or actually, excuse me, the transformations for square root functions are have the same characteristics and the same way of writing them out as like the square root functions. So if you need to reference that chart from 10.1, I encourage you to look back at page 545 in your textbooks. So if there is some shifting or if there is some change in the vertical horizontal stretch or shrink, uh, we can look at that. So here they're asking us to graph the function and they want us to compare it. So comparing it, again, I referenced that square root transformations. It'll give you the same thing. But what we're going to do is this. So first off, if I make my table, again, I'm just going to pick um, -1, 0, and 1 as my values. Square root of -1, I'm sorry, cube root of -1 is -1 minus 4 is going to give me a -5. Cube root of 0 is 0, and then it's going to give me -4. Cube root of 1 is 1, and this will give me -3. So plugging it into the table. So basically what we look here when I have this graph is I go to -4, and that is where my graph sort of changes. So if you look, -1, -5, somewhere right here, 1, -3 is somewhere over here. So my graph is going to look something kind of like this. You know, and again, you can check it if you have graphing calculator capabilities to see if that does in fact hold true. When they want us to compare it, looking at this, there's neither a stretch nor a shrink for vertical. We can say that it translates that it moved down 4 units. All right. So again, these are other functions, other cube root functions. And I would say like number one is very similar to how the example we just did. If you were to look at, say, um, this example here, and we're just trying to graph it, basically where the graph will kind of shift, it would be at essentially 5, 0. So like if I had my 5, 0 here, it would look something kind of like this, and then it would kind of move in here. So still my, domain range would be all real numbers. The comparison here with our apparent cube root function is it would just move to the right 5 units because h was 5. And then for like number 3, because you had that 4 on the outside, the 4 on the outside means is that it's going to have like a vertical stretch of a factor of 4. And basically what it means is it's still going to be, crossing at that 0, 0, but it's just going to be a little bit wider than um, than that apparent function. It would look, parent function would kind of look something like this in comparison. If you had a negative on the outside like we do here, this is where, you know, in comparison, you know, if we had our parent function looks something kind of like this, where it kind of crosses through coordinates 3 and 1, but with like this one, well, I noticed that h is -2, so you're going to go -1, -2, where it's going to kind of cross here. But because of the negative, you're going to start in quadrant 2 here, and then kind of go in like so. And in this case here, you're reflecting over the x-axis because of the negative on the outside. And because h is -2, you actually move the graph 2 units to the left. With a graph like this, there's a bunch of values here, but again, really it's trying to figure out, where your graph kind of, makes that change. And in this case, since h is 3 and k is 4, so if we try to graph this, looking at cube root of x would look something kind of like this. Well, this one here, because we have that vertical stretch of a factor of 2, and h being 3 and k being 4, that means you're going to move your graph 3 units to the right, and you're also going to move the graph 4 units up. So I'm just going to go 1, 2, 3, 1, 2, 3, 4. So that is kind of where that change is going to be made. And again, because it's a vertical stretch, it'll look a little bit wider, and it'll kind of look something kind of like this. And again, you can, make a table and um, pick those values. What I would suggest when you are making a table like this, and there's a shift in this point right here, I would try to make values to the left of that point. Make sure you have that point and something to the right of it. So like, for instance, since this is 3, you could say something like 2, 3, and 4, and then kind of go from there. Last slide here, we're going to look at is dealing with, it says the graph of cube root function m is shown. They want us to compare the average rate of change of m to the average rate of change of h of x equals the cube root of 1/4 x over interval x equals 0 to x equals 8. So first thing you are going to do is you are going to calculate the average rate of change using points whose x coordinates are 0 and 8. So if you look at x is 0, which is right here, and you look at x is 8. So in this particular graph, we are looking at values of, or at least those coordinates of 0, 0 and 8, 8. Now, we are going to use those coordinates and create an average rate of change for m. So in this case, what we're going to do is you're going to take your 8 and subtract it by 0, and it gets divided by Same thing would be 8 minus 0, which is going to be equal to 1. The next thing you're going to do is you're going to evaluate your function h of x with those values of x. So you're just going to substitute in 0 and 8 and see what you come up with. So in this particular instance, so if I put 0 in for that, so if I got the cube root of 1/4 times it by 0, 0 times 1/4 is 0, this is going to equal 0. If I were to put in the cube root of 1/4 times it by 8, I get the cube root of 2. The cube root of 2 is approximately 1.3. So now what we're going to do is now we're going to take and use those values to create a difference in the rate of change. So what we got here is you're going to take this value here, which is 1.3, and subtract it by 0, and it gets divided by those x coordinates, which is 8 minus 0, which again, this is going to be 1.3 divided by 8, and that's going to get us about 0.16. All right, so to figure out finally the rate of change between x is 0 and x is 8, what we're going to do is we're going to take this value here, which is 1, and divide it by this value here, the 0.16, and we get a value of 6.3, okay? What that means is the average rate of change of m is 6.3 times greater than the average rate of change of h over the intervals of x is 0 and x is 8. And that is being able to graph cube root functions. I hope this helps. Until next time.